Hey guys, I want to go over some things with you about how to accept or reject a null hypothesis. Technically, the terminology is reject or fail to reject, but we usually say just accept the null hypothesis. Remember that your null hypothesis is essentially the assumption that nothing has changed. And an example of that would be, let's say a few years ago, we measured the average height of students in PD Bio 120. And that height we found to be, what the X bar right here was 68 inches. And then in the new class, right now in this class, let's say we took the average and it was 69 inches. Well, we need to see what's going on here. So we see basically from these basic numbers that, yes, this class on average is taller than the old class. But is that a significant finding with a 1-inch difference? That's what this equation is going to tell us. So based on a couple of variables, which are standard deviation and our n, which is our number of observations, we can find out how much error we have in these averages, right? So to find out if we have a significant difference or a meaningful change from the old to new, we need to calculate this out. So I'm going to do this live. So we need, first of all, the n, which is the number of observations, and then the s, the standard deviation. Now remember that your standard deviation is calculated using a different equation. And you may remember this equation from your nightmares, but that is separately calculated, or it can be given to you. It just depends on the problem you're trying to solve. So what you want to do to be able to do this is, well, calculate your standard error of the mean. And we'll take for the old, your standard error is equal to your standard deviation simply divided by the square root of the number of your observations, which in this case, in the old class, we had 120. Now, there's mathematical reason to all of this. So if you notice, your standard error will get smaller if you have a lot of students, because if we take a lot of students, we're pretty confident that the average is going to be more representative of the truth. Than if we only had, let's say, 5 students, we might get a really big standard deviation if this denominator was 5, and that would make the standard error pretty big if the denominator here was pretty small, the number of students. So few students means a big potential error in the average that we get for the class. So let's go ahead and calculate this. So for the old class, we had 120 students, and let's see, 2.2 divided by square root of 120 should be 2.0. Oh, excuse me, that's not correct. It should be 0.2. Okay, approximately. So that's your standard error of the mean. Remember what that is. Standard error of X bar. Okay, now for your new standard error, we have this 1.8 divided by the square root of 162. Same process. Pretty simple. Let's find out what that is. 1.8 divided by square root of 162. That should be 0.14 approximately. Okay, that is your standard error of X bar, or your mean. All right, so now that we have these numbers, what does that even mean, right? And I get these kinds of questions all the time when students ask me about statistics. What does this mean? What do we do with this standard error of the mean? Okay, this standard error of the mean doesn't mean squat unless you have a mean to attach it to. So the mean for the old class was 68 inches. And for the new mean, we have 69 for our current class. So what happens is we do a plus or minus the standard error of the mean. So 0.2 and then 0.14. Okay, now you can already kind of see, we want to see if these will make intervals, right? These will make ranges of potential actual values. We do standard error of the mean just because by virtue of just the nature of taking an average of a sample, we will have some natural variation. So we need to account for that. So depending on how much if we know our population or our sample isn't going to vary that much, we're going to have a pretty low standard error of the mean, and we're going to have a really small range. So since we had pretty big classes for both, we actually have pretty small standard error of the means. And so the range of this one is going to be 67.8 to 68.2. So you should kind of already be able to see that these really don't overlap at all, because the other one would be 68.86 to 69.14. Now notice that these two intervals do not overlap. So that means even with the potential natural error in the sample, which we account for with the standard error of the mean, even accounting for that potential error, there's no overlap here. So then we can say, hey, look, this new class actually looks like it is taller significantly than the old class, and this isn't the same old class that it used to be. So we can reject the null hypothesis that our class is just the same as the old class. So normally we would expect that the average wouldn't change. So then if you want to continue this experiment, you would start looking into other potential variables that would affect this. But for now, we reject the null hypothesis that the old class standard is the same for the current standard. So hopefully that made sense. And keep watching the videos if they're helpful. Thanks, guys.